Good morning, good afternoon, or good evening, everyone, wherever you are located in the world. And thank you for joining us for this AMETEK Solid-State Controls, Understanding UPS and Semiconductors webinar. As always, just like to ask before we get started, if you can hear my voice, please go to the right-hand side of your screen into the chat bar and let me know that you can hear me. As always, I don't want to be speaking into the internet and not have anybody hear what I'm saying. So please let me know if you can hear me by typing in the chat bar. I'll wait for some answers and then we will get going. Thank you, Wyatt. I appreciate the answers. Carlson, Jonathan, Val, thank you very much indeed. So let me do some introductions. First of all, my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls, and I'm located in the Stafford office, which is on the southwest side of Houston, Texas. Don't be fooled by my strong Louisiana accent. I am from Texas. Only kidding, I'm from Scotland originally. I have over 20 years in the industrial UPS industry. I started my life working on UPSs in the oil and gas sector of the North Sea in Scotland. And then 12 years ago, I moved to the US and I've worked in the Gulf Coast. Originally, I worked in the field and now I'm the Senior Technical Manager for AMETEK Solid-State Controls. I've worked with all the major UPS charger manufacturers, so I'm very familiar with everything that is out there. There will be a lag of around it's between 15 and 30 seconds. As I always explain, Webinar Jam is a platform that we use for the webinar, and they have to convert what I am saying and displaying into Android, iOS, and Windows formats, and then send it out all over the world. So it does take between 15 and 30 seconds between me saying something and you hearing it. So therefore, I'm only going to see people type about 15 to 30 seconds after I have said something. So for that reason, I tend to leave the Q&A until the end. So if you do have any questions, feel free to type them in whenever they pop into your head. And it would be appreciated if you go into the chat section. If you have questions, type it into the Q&A only tab, not the chat tab. That way, when I get to the end, I can go through all the questions one by one. Webinar Jam has a panic button. So if something happens, if I see everybody say that they can't hear me or something seems to go wrong, then I can press the panic button. A new room is created. We all get invited and put into that room, and then we can continue from where we left off. A very popular question that everybody asks is, will the webinar be recorded? And the answer to that, as always, is yes, it will be. Webinar Jam does record the webinar. And for everybody that has registered for the webinar, if you're watching this right now, that means you registered for it. That means you will receive a link for the replay. The problem with the Webinar Jam replay is that it treats itself like another webinar. In other words, you press play and that's it. You have to watch it from start to finish. You can't fast forward, rewind. I think you can pause, but you can't go to specific parts of the webinar. So what our fantastic marketing team do is they go into the webinar platform, download the video, convert it to an MP4, and then upload it to our AMETEK Solid-State Controls YouTube site and on our channel by tomorrow at the latest. London's put the link in the chat bar there. By tomorrow at the latest, that video will be available and you can then share that video. You can pause, rewind, do whatever you want. It is free to everybody out there. And it's also a good place where you will find every other webinar that we have done in the last 2 or 3 years that we've been doing this webinar. So it's a very good place to go and find out some more stuff. And finally, the webinar should last round about 1 hour, depending on how much I talk. So hopefully we can keep it to 1 hour because I know your time is precious. So The learning outcome should be understand the most common semiconductors that are used in the industrial UPS systems, understand how each semiconductor works, discuss power flow and general operation of each semiconductor, and then discuss the advantages and disadvantages of different semiconductors if we have time. Okay. I'm having issues with my pen that I usually use to draw on the webinar, so I might not be drawing today. It's a little bit offset. So I'd like to start off with the absolute basics. So the way that we use semiconductors, and we as in AMETEK Solidstate controls in our UPS systems, pretty much is always as a switch. Okay, we don't use it in its linear amplification range and do some fancy things with it. It's either on or it is off. So it is really like a physical switch, except for a switch has moving parts. A semiconductor has no moving parts. The switching is done within the layers of silicon. So I have this very basic drawing on the screen for you, and you have on the left-hand side a DC power source. The positive is at the top of the power source, and the negative is at the bottom of the power source. And then the most simple circuit diagram you could probably ever see. At the top, there is a switch, which is open at this moment in time. And then on the right-hand side, there is a lamp. And obviously the lamp is off just now because the switch is open. The potential or the voltage from the DC source cannot get to the lamp because the switch is open. Okay, so the lamp cannot light. And obviously, if we then, on the next slide, close that switch, that allows the voltage from the DC source to get to the light. Current will flow and the lamp will light. So open, the lamp will not light, and closed, the lamp will light. Very, very simple. So if you get your head around that, then you should be able to figure out what I'm going to say with semiconductors. So the first semiconductor we're going to talk about is a diode. Okay, now a diode has an anode and a cathode. And the anode in this drawing here is on the left-hand side. So I like to see, you know, when you look at a diode symbol, that triangle, I like to view it as a funnel. It's pulling the current in, it's focusing the current into the diode, okay? And then the right-hand side, there is that straight line, which is the cathode, okay? Now, that triangle is pointing left to right. So that means it will allow current to flow from left to right. In other words, if you put a positive on the anode with respect to the cathode, then current will flow, okay? And if you try and put current the other way, if you put a positive on the cathode with respect to the anode, then the diode will block the current, so it can't flow from right to left. And the most popular question I always ask when we're doing our in-person classes is, what is the mechanical equivalent of a diode? And the answer on the page here is a check valve. I'm just going to take a drink. So this check valve on the screen here, you can see the arrow on the left-hand side. If you have fluid flowing from left to right, that will push that flap open and will allow the fluid to flow through this valve. And then if the flow of that fluid changes and it tries to flow back from right to left, then that will push that flapper down and it will prevent the flow from right to left. So it is pretty much identical to a diode physically, but obviously a diode is done using electrons and semiconductors rather than a flapper and fluid. But it's just to give you a better understanding of how a diode actually works. Okay, so if we put that diode in instead of the switch, and you're going to see a theme as we go through these slides, I'm going to replace that switch that we had in the original easy diagram with all of the semiconductors that we use inside a UPS system to show you how they replace that switch. So as you can see, with the DC power source, the positive is at the top, the negative is at the bottom. So that means the anode is going to be more positive than the cathode. So that means this diode is going to conduct, because that's exactly what we need for the diode to conduct. The pressure is from the left to the right, anode to cathode. So therefore, the current will flow and the lamp will light. But conversely, if we put the diode in the opposite way, you can see the power source hasn't changed. We still have positive at the top and negative at the bottom. But now the cathode is more positive than the anode. And the diode says, no, I'm not going to allow current to flow. That's not how I operate. I need my anode to be more positive than the cathode to be able to conduct. So in this circumstance here, the lamp will be off. Hopefully that makes sense to everybody. Now, we've slightly changed the diagram now. We still have a diode, we still have a lamp, but now you can see on the left-hand side, we have an AC power source rather than a DC power source. And that's going to change things for us. And I'll show you what happens when we have an AC power source. Okay, we're going to connect an oscilloscope to the lamp. So that's what you see in the center of the screen. So the top waveform, the yellow waveform, is the AC power source, and the green waveform is what you will be seeing across the lamp. Okay, now you can see that the AC power source is pointing towards the positive half of the sine wave at this moment in time, and that's what the positive half of the sine wave. Okay, and you can see for this positive half of the sine wave, that means the power source is more positive at the top than it is at the bottom. So that means the anode is going to be more positive than the cathode. So therefore, for the positive half of this sine wave, when the anode is more positive than the cathode, it's going to allow that whole sine wave through, that whole portion, top half portion of the sine wave. Okay, because everything is as the anode is looking for. It's looking for the anode to be more positive than the cathode. Now on the next screen, you can see on the left-hand side, the power source is now flipped because we're now looking at the bottom half of the sine wave. And now the bottom of the AC power source is more positive than the top half. So it's trying to drive current in the opposite direction. Just like the flow on the check valve has changed direction. And the diode says, no, I'm not going to allow that to happen because you now have my cathode more positive than my anode, and I don't conduct electricity in that way. So it says, no, I'm not going to conduct, and therefore the lamp will not light. So in this circumstance, you're only going to get, if you put the yellow waveform into this circuit, on the output of the circuit at the lamp, you're only going to get this green waveform. The positive half of the waveform is only going to be allowed through. And another question I like to ask in the live classes that we do here in Stafford is that bottom green waveform DC? I'll let you think about that for a moment. Oh, got ahead of myself. And the answer is yes, it is DC, because DC means direct current. The current is only flowing in one direction. Now, you can say, but it's changing amplitude. Yes, it is changing amplitude, but it's just, that's how much current is flowing, not which direction it's flowing in. Okay? So it's only when the waveform goes negative that the current will reverse direction, and we stop that by using the diode. So therefore, only the top half of the waveform gets through, and that is pulsating DC, but it's still DC because the current is only flowing in one direction. Now, here's an example of some of the diodes that we use inside our UPS systems. They could be rectifier diodes, they could be inverter diodes, they could be static switch. Actually, we don't use static switch diodes. But this is what they look like. And you can see on each of the bodies of this, there is actually a symbol stamped telling you which side is the anode and which side is the cathode. So for this diode here, the left-hand side is the cathode and the right-hand side is the anode. Okay. And then you also get multi-packs. This actually has 2 diodes inside it. And both the cathodes are connected together on terminal 2. And the anode for the first diode is on terminal 1, and the anode for the other diode is on terminal 3. It's called a semi-pack when you buy them from Semicron. But you can see there's 2 diodes in there, and we can use these packs to build diode bridges and things like that. So the next semiconductor we're going to talk about is the SCR, which is a silicon controlled rectifier. In Europe and Asia, they may be called thyristors. They are both exactly the same thing. It goes back to Kleenex or a Hoover for a vacuum cleaner. It's just the thyristor was the most prominent manufacturer of SCRs when they first originally came out. And it just got picked up, and a lot of people call an SCR a thyristor because that's what they were. One of the original manufacturers called their SCR was a thyristor. So, but they are interchangeable terms, SCR and thyristor. And it's exactly the same as a diode. We still have the anode and we still have the cathode. The anode on this picture is on the left-hand side. The cathode is on the right-hand side. But now we have added a gate terminal. Okay, this additional gate terminal allows us some flexibility. It allows us to tell the SCR when to turn on. So everybody says, okay, do you have a mechanical equivalent for this? Well, really there isn't a mechanical equivalent. So I've designed a special check valve to hopefully explain how it works. So it's still the same. We still have the anode on the left and we have the cathode on the right. But you can see down the bottom, we have added this gate. Okay, and as you can see just now, it's preventing the flapper from moving. You know, in either direction, it doesn't matter which way the current flows, that flapper is not going to move. So the fluid cannot get from anode to cathode or from cathode to anode. So when we don't have a gate signal, when we're not sending a signal to turn it on, it will not conduct in either direction. It's like an open circuit. It's like an open switch. Only when we remove the gate does it allow it to start behaving like a diode. So we're going back to the original drawing that we had. So now instead of a switch and instead of a diode, we now have an SCR. And with the SCR, we need to be able to send a signal to its gate. So you can see we have tapped off the top of the DC power source, and we now have a switch which is open just now. So we are not sending a gate signal to this SCR just now. And therefore, okay, we do have positive on the anode with respect to the cathode, but power does not flow through because we're not sending it a gate signal. So the lamp will be off. I hope that makes sense. It's only when we press switch 1, that push button, and we send a gate signal to the SCR that we will say, okay, now you can behave like a diode. That's really essentially what the gate lead does. It is giving the device the permission to be a diode. So hopefully I can explain that over the next one. Now, you can see now what I've done is I've turned the DC source upside down. So we're now trying to force current in the other direction. And we don't have the switch pressed down, switch 1. So therefore, it's not going to conduct, and we have positive on the cathode with respect to the anode. So if it was a diode, it still wouldn't conduct. So I just want to show you that in both forms, positive on the cathode with respect to the anode, or positive on the anode with respect to the cathode. If you're not sending a gate signal to the SCR, it's not going to conduct in either direction. It's only when you push switch 1 down, and you can see now that we have pushed S1 down, SW1, and we are sending a gate signal to the SCR. It's now saying, okay, you can be a diode, and therefore, if you have a positive on your anode with respect to your cathode, we're going to allow current to flow and the lamp will be on. And importantly, it will stay on. And this picture here, you can see that the gate drive has been removed. So we have removed the gate drive, but because we still have positive on the anode with respect to the cathode, this will stay on forever. As long as that DC source has voltage potential and it's still driving current through the device, the SCR will stay on forever once it has received a gate signal when it's connected to a DC power source. So the important thing to remember is if you get a gate drive, and then from that point onwards, if the anode stays positive with respect to the cathode, the SCR will remain on indefinitely, absolutely indefinitely. And the only way when you are supplying the SCR with a DC power source to stop it conducting is to stop the current flowing through it. Okay, and in this circumstance, you can see on the top left here, we've inserted a switch, we've opened the circuit, and that has stopped current flowing through the SCR. So now the lamp will be off. You have to stop the current flowing through the SCR either through electronic forms, with a relay, with a switch, whatever it is. You have, with the DC source feeding that SCR, you have to break the current going into the SCR to stop it conducting. And I think we'll get to it later, but the important thing to remember is if you are using an AC power source, every time that AC waveform passes the zero crossing point, and we'll get to it in a slide that we do later, then the current stops because there is no potential at the zero crossing point on a sine wave. There is no potential either side of the power source, so current stops flowing through the SCR and it switches itself off. And then it waits for a signal to be turned on again. And that's how we control our rectifier SCRs. And we'll get to that in a moment. And here's what SCRs look like. You can see compared to a diode, they're very similar, but they now have small red and white leads coming out of them on the stud mounted ones and on the hockey puck ones as well. That's the white lead is the gate lead and the red lead is the cathode. So we always want to supply power gate cathode to turn it on. And in the bottom left hand side of the picture, that's two different versions of multi-packs. and the gate leads would be connected to the right-hand side terminals. They're push-on terminals on the right-hand side. They're those small push-on terminals. And then the last device of choice that we're going to discuss today is the transistor, and in particular, the IGBT, which is the insulated gate bipolar transistor. And there's two drawings on the page here. The one on the left, that is the basic drawing of an IGBT. You have a gate, and importantly, you've got to remember the gate is actually not physically connected to the collector emitter. You can see there that there is a gap, and that's where the term insulated comes from. The gate is not physically connected to the collector emitter junction. It's completely insulated. So that allows us to do some pretty cool things. And then the collector emitter is where the main power will flow. And on the right-hand side, all they've done is they have, and with nearly all IGBT manufacturers, built into the IGBT will be this reverse connected diode across the collector emitter. The anode will be on the collector, and the cathode will be on the collector, and the anode will be on the emitter. And it's basically, I call it a freewheeling diode. It allows, when this IGBT switch is off, there will still be current flowing through it. And as with any form of electrical circuit, there will be a back EMF because there's some inductance in there. Whenever you switch off current, when there's current going through a device, there's going to be a back EMF, and that diode allows that back EMF to discharge into a capacitor bank and prevents the IGBT from blowing up, basically. That's what that diode is for. So most IGBT manufacturers have that diode built into the device itself. And the most basic way to describe how an IGBT works is the hand is the gate signal, and then we have the collector emitter junction. Okay, so if we are not sending a gate signal, in other words, we haven't pressed that spring-loaded switch, then the collector emitter junction is open. It's like an open switch. Very, very simple. And then if you press that spring-loaded switch, then the collector and emitter circuit will be made, and it will be a closed switch. And then obviously if you remove your finger again, because the switch is spring-loaded, it will open automatically again. So the main difference between an IGBT and an SCR is you can turn an IGBT on and off whenever you want. You don't have to wait for the zero crossing of the sine wave. As soon as you remove the gate signal, the IGBT will turn off. Okay. And another circuit equivalent is a solenoid controlled valve. So on the left-hand side, you can see that we've got our gate where the coil and the armature is at the top. We've got our collector on the left-hand side, and we've got our emitter on the right-hand side. And with the gate off, which is the left-hand drawing, fluid cannot flow through because the plunger is down, and it's stopping the fluid from flowing from the collector to the emitter. Now, if we send a gate signal, so the drawing on the right-hand side, then the coil energizes, it magnetizes and pulls the plunger up. And you can see fluid can now flow from the collector through to the emitter. So that's the gate on. And then obviously if we remove the gate, the plunger would drop down again and stop the flow again. So hopefully that gives you more of an understanding physically of how an IGBT works, a representation of how physically it works. So now we have that simple drawing, and instead of having a switch, instead of having a diode, instead of having an SCR, we've now replaced it with an IGBT. You can see on the drawing that switch 1 is open, so we're not sending a gate signal to this IGBT. So therefore, power cannot flow to the lamp. The lamp will be off. It's just acting as a switch, and the switch is off. Now, if we press switch 1, that sends a gate signal to the IGBT, and it turns it on and allows power to flow from the collector to the emitter. And the main power flow goes through the lamp back to the DC source, so the lamp will be on. And then if we open the switch again, the gate drive has been removed, and immediately the IGB turns off again, and the lamp will turn off. So IGBTs are very simple. You send a gate signal to it, it becomes an on switch. And if you remove the gate signal from it, it becomes an off switch. And these are the types of transistors that are inside our inverter bridges. Some of them are single packs, some of them are dual packs, but you can see on the main terminals are the 3 terminals that you can see on both pictures, and there's 2 IGBTs in each of these packs. And then on the right hand picture you can see the terminals for the gate terminals there. You would need to put your gate wires on those prongs that are sticking out from the IGBT. So how is each device used when it comes to UPS systems? That's always going to be the question. So for a diode, we use them in rectification. Rectification is how we change AC into DC. And you can see on the left-hand side here, we have a full sine wave going into a transformer. That transformer is just giving us isolation. Just really forget about that in this drawing. It's just the AC into that transformer is the same as the AC out of that transformer. Okay. And only you can see that on the right hand side, we're measuring across that resistor, across the load terminals. We're only getting the positive half of the sine wave, because this diode, as when we went back to that original drawing, is only allowing the positive half of the sine wave through. Okay. And I asked this question earlier, is this DC? And it is DC. We have rectified the AC on the left-hand side to DC, because we are no longer having current flowing in the reverse direction. Current is only flowing in that direction. See, I'm trying to use my pen and it's just not working today, unfortunately. So in a full wave, that was a half wave rectifier. And obviously we're wasting half of the waveform there, which is very, very inefficient. So now we have a full wave rectifier, and we've got our AC waveform on the left-hand side. The positive half is red and the negative portion is blue. And I always draw these 2 full wave rectifier bridges because they are identical. The one at the top is what near enough all industrial UPS manufacturers use, how they draw their rectifier bridges. The one on the bottom is what most of the schools teach. You know, when I went to university and I studied electrical engineering, that the bottom bridge is how I learned diode bridges. But the top one is what most industrial UPS manufacturers work. But they both work identically, and I'll show you how. But what you can see is on the left-hand side, it's saying sine wave in, it goes through a rectifier, and on the right-hand side, it says equals. The load will see this waveform here. We have the red portion is the positive half of the waveform, but now we have the blue portion rectified as well. It's been flipped above the 0 volt line, and it's been rectified. So all the current is flowing in one direction now. And I'll show you how that works on the next slide. So for the red, for the positive half of the sine wave, the top of the power source is more positive than the bottom of the power source. So you follow that red bold line and the arrows, and you can see that it goes through the red diode. It can't go back down through the blue diode because the cathode is stopping it doing that. So it goes out through the load resistor and it gets back to the bottom of the power source through the other red diode. Okay, and on the right hand side you can see that allows the top portion of the waveform through to the load circuit. And then when the negative half of the cycle, then the positive is now on the bottom of the power source with respect to the top of the power source. So if you follow that blue line and the arrow, it now goes through that blue diode and it flips it up to the top, and then it returns to the top of the power source, which is now more negative, through that bottom left diode. And that flips the blue waveform up above the 0 volt line. So we now have both the top and the bottom half of the sine wave flipped up above the 0 volt line. So now we've converted it all to DC. The full wave has been rectified in this circuit. But there is a constraint with that. Yes, this is AC on the left, DC on the right. We have done what we wanted to do. We have a rectifier. We have rectified AC to DC. But the unfortunate thing is we are restricted on the control of the output, what the DC value is, by what the input is. So for ease, in the US, we use 120 volts AC as our single phase that you would find in a socket in the wall that you plug your appliances into. The peak of that waveform is 170 volts AC. Okay? So when you convert that line over to the right-hand side, you will see that the peak is going to, of all of those rectified waveforms, is going to be roughly 170 volts. Okay? Mathematically, though, the average DC voltage, and this is the equation that you use to find the average waveform, the average DC from an AC waveform is 2 times the voltage peak divided by pi, so which is equal to 108 volts DC. So the average DC voltage when you put 120 volts into the system is going to be 108 volts out. But if that voltage goes down, if the AC input voltage goes down to 100 volts, that means the peak goes down to 142 volts, which means the average voltage has now gone down to 90 volts DC. Okay? And if it goes up, it would go up the other way. So the way that we can adjust for varying AC input voltages is, instead of having all diodes, we can now add 2 SCRs, and that gives us some control. Because if you remember what we said, we can turn the SCR on whenever we want, and then when it gets to the 0 crossing point, it always turns itself off. So you can see on the left-hand side there, we've still got our AC waveform going in. In the middle, we have our rectifier bridge, and the 2 devices at the top now have gate signals, so they're now SCRs. And the waveform on the right, depending on when we switch the SCR on, we can switch it on early in the sine wave, which is what that first red waveform is. We can switch it at the exact half peak of the negative sine wave, and you only get half the waveform going through. The next red one is we're switching on very, very, very late in the cycle, and you're only getting a tiny bit of the waveform through. And then the last blue waveform is we switch the SCR on very early in the sine wave, and we're allowing that portion of the waveform through. So we now have control of how much of the AC waveform we rectify that gets out to the DC side of our bridge. Okay. And we go back to our drawing here. Okay. If we turn on the left-hand side, you can see here, we're sending the gate drive signal at this point here, where that arrow is pointing to. That's when we turn the SCR on. Then that is the only portion of the waveform that is going to get through on the right-hand side, measured across the load. So even though we have 2 half cycles on the positive side and 2 half cycles on the negative side, on the left-hand side from the power source, we're only switching the SCR on the second red portion of the sine wave and halfway through the sine wave. So the right-hand side that's the only portion of the left-hand sine wave that's going to get out to the right-hand side where the load is connected. And then once that sine wave gets down to the bottom and crosses the 0 volts line, then it's waiting for its next gate signal. So an SCR can regulate the output for a changing input or higher load demand. So basically, we're saying when we went down to 100 volts on the AC input, that's a peak to peak of 142 volts. So let's say, for example, if we knew that the input was going to be 142 volts, we would switch our SCRs on at exactly half waveform. And if you took the mathematical average of that right-hand side, then let's say, for example, we want it to be exactly 100 volts DC, then that's what this control is doing. We can regulate that DC waveform. The mathematical average of that right-hand waveform would be 100 volts DC exactly. And if we had 120 volts input, where the peak goes up to 170 volts, you can see that we've switched the SCRs on a little bit later in its half cycle. We're now not right at the top of the peak. We're a little bit further into the waveform, but that maintains our output at 100 volts DC. We are regulating the output now because we can turn those SCRs on whenever we want. And then if we had really high input voltage, the peak went up to 190 volts, then we're turning the SCRs on really, really late in the cycle to maintain that 100 volts DC on the output. And that's why we use SCRs in our rectifier bridges, because we don't know, if we send a charger out, the nominal rating of that charger is going to be 480 volts 3-phase. But we don't know if your plant's voltage is 480 volts. It could be 500 volts. It could be 460 volts. They're all over the place depending on your transformer windings, how far away the piece of equipment is from the transformer. It goes through an MCC. So we have to be able to say, okay, our charger is going to give you, for a 60-cell battery, 135 volts DC out. And to do that, we have to constantly turn these SCRs on at certain points in the waveform to maintain that 135 volts DC with the varying AC input voltages within the parameters of what our rectifiers will accept. So that's how an SCR can regulate the output from a rectifier. Now, for IGTs, we use the IGBTs in an inverter bridge. In the majority of cases, our inverter bridges are IGBT controlled. So what we do is we take the DC, now we're converting the DC that we've created back into AC. And it's a little bit more complicated to get your head around. But what we can do, with the gate drive removed, you can see that on the right-hand side, where we used to have a lamp, we now have a transformer, okay? And if we're not sending a gate drive signal to the IGBT, nothing is going to get to the transformer. So the output waveform is going to be 0, nothing. Okay. But if we send a quick pulse to the IGBT by pressing S1 quickly, then we will get a pulse on the output. And that pulse will have the peak voltage of the DC source on the primary of the transformer. And if it is a 1-to-1 transformer like we have drawn here, then the secondary is going to have a voltage of the peak voltage of the DC source. So let's say this battery, the DC source, is a standard lead acid battery in America. They're usually 60 cells. We would have that charged at 135 volts DC. Then the peak of this pulse is going to be 135 volts DC. And then what we can do is we can change the width of the pulses. So obviously we're not changing the amplitude because that's coming from our rectifier bridge, and that's 135 volts DC. And in truth, we're not changing the frequency either. If you look carefully, the center of each of these pulses is exactly the same space apart. So the frequency is not changing. What we are doing here is we are changing the pulse width, and that's where the term pulse width modulation comes from. We can change the width of each pulse. And I know this is jumping from the previous drawing to this drawing is a little bit more confusing, but now what we've done is we have put 4 IGBTs in a bridge. We still on the left-hand side have our positive and negative, and we still have our transformer, but now what we've done is we've put it in an H bridge arrangement so we can change the DC into a pulse width modulated AC. Okay. Now, so if we have transistor pairs A on, you can see the red flowing from the positive to the negative makes the top of the transformer positive with respect to the bottom half of the transformer. Okay, so the power flows from the positive down through transistor A, through the transformer, down through the other transistor A, and back to the negative terminal. And the waveform on the right-hand side, you can see the pulses are getting wider as they go through, and then they're getting narrower again when they get to the end. And in truth, the mathematical representation of that pulse width, if you did a mathematical calculation of the average voltage of that waveform, it would approximately give you a sine wave. And then what we have is the inductance. There is an inductor before the transformer here, and there's also a capacitor on the output. That smooths out that pulse width modulation and turns it into a perfect sine wave. So that's the top half of the sine wave we have just created on our inverter bridge. Now, before I go to the next slide, remember the positive is at the top of this transformer and the negative is at the bottom of the transformer. But now what we're going to do is we're going to switch transistors B on. And you can see, follow it from the top, the positive symbol, follow it down. It goes through B, and now we have the bottom of the transformer is now more positive than the top of the transformer. So we've now created the opposite side of the waveform on the output of the inverter bridge. And we're still pulse width modulating on the bottom, and the mathematical average is still a sine wave. Okay, so that is how our inverter bridges work. We're just switching pairs IGBT pair A on and then IGBT pair B on at 60 hertz. In the grand scheme of things, that's what we're doing, but actually all these pulses means we're switching at 8 kilohertz. But it's still the same principle. And then the output of that system, you're going to have the red pulse width for the positive half, the blue pulse width for the negative half, and you can see that sine wave imposed on there. That's actually what you're going to get out of the inverter. So on the primary of that output transformer, you're going to have the pulse width modulated signal, and on the secondary of that transformer, you're going to have that perfect sine wave that's the hashed line that's drawn or imposed on this waveform here. So now we get to a point where we can ask if there are any questions. So I'm going to go to the Q&A. And I only have one question so far. So while I read this question, if you have any other questions, please type them in so I can answer them for you. So Bryce says, is there a breakthrough voltage threshold that can be reached on an SCR that would overcome the SCR gate? And in truth, yeah, I always speak in relative terms, or for ideal SCRs or transistors where we're staying within the parameters of what the manufacturer of the SCR designed it for. But for everything, there is a breakthrough voltage on the data sheet for the SCR for the anode to cathode or the cathode to anode. And there is also a voltage that you have to stay between for the gate signal as well. So yes, there will be a voltage, especially cathode to anode. If you exceed that voltage, then you can break down the diode or SCR, and it will basically become a short circuit. It will, most SCRs fail short. So if you do impose a voltage out with the rating of that SCR, it will be damaged. But all UPS manufacturers design their systems so that should never happen. So hopefully that answers your question, Bryce. I don't see any other questions coming in. I've either bored everybody to tears or I explain things so well that nobody has any questions. I'll probably say the first one is more relevant. Oh, do we have another one? I think we do. Bryce says thanks. So what I'll do, if there are no other questions coming in, I will start to say thank you very much for attending this webinar. We do appreciate you taking the time out of your day to watch these. We know you are very, very busy people, and for you to take 50 minutes out of your day to listen to me ramble on is very appreciative, and hopefully you have learned something. Don't forget that the webinar is recorded. It will be posted to our YouTube channel by tomorrow. Our marketing department will post the link in the chat bar. Let me see if it is in there yet. Yes, it is. London has posted that in the chat bar for you. So it will be available within the next 24 hours, and you can share that to your heart's content. Where there are no restrictions on you sharing any of the videos that we have created out into the world. You can also, if you have any questions that you think of after this webinar, then or if you need assistance in the field with any of our UPS systems, you can go to our website and go to our Contact Us link, which London has posted in the chat bar. You can call our 1-800 number, which is always answered by a human. And you can also go to sci.marketing@ametek.com, and you can send them an email and they will direct it to the correct person. So if there are no other questions coming through, once again, thank you very much. You will receive a survey after this webinar is complete. We do read every single survey. We want to know what you want us to discuss at our next webinar. So if you have a particular topic you would like discussed, whether it's battery chargers, batteries, troubleshooting inverters, whatever it is, if you can think of something that we haven't covered yet that you would like us to cover, please do reply to that survey. One of the questions is, what topic would you like to see next? Fill that in. I read every single one of them. And if it's a good idea, I will create a presentation and do it next month. So please do fill in those surveys. So for once in my life, I have finished within the 1 hour time limit. That's amazing. I don't think I've ever done that before. So thank you very much again, everybody. Take care until next time. And for those in America, have a wonderful Thanksgiving next week. And I will speak to you next month. Thanks very much. Take care.